Alright, so coming back into the examples for our solids of revolution or solids of rotation, that again just kind of recapping where we finished the last time, we are always going to take a two-dimensional function or relation. We are going to spin that two-dimensional function around an axis, either a horizontal line or a vertical line, and when we spin it, we will create a solid of revolution. That solid will then be sliced into slices of bread, which will always end up being discs. We will calculate the volume of each disc by finding area of the base times the height, and then we will add them up and it turns into a Riemann sum, and that will be our estimate for our volume. So let's take a look down here at example 2. And the best thing, just like with areas, the first thing that you should always do is sketch, sketch, and sketch, because you've got to understand what's going on. Now, when you're looking at problems such as this, you also it does help to be pretty decent at sketching, because you want to be able to clearly be able to tell what's going on. So we're going to have a region. That region is bounded by the square root function, square root of x, by the x-axis, so I'll just kind of highlight down here so I can see where I'm at, the x-axis, and x equal to 1. So here is going to be the region that I'm going to start by rotating. And I like to, having a colored pen is always kind of nice on this, because I like to highlight the region that I'm getting ready to spin. Okay? The second thing that I would do when you are doing these problems is I would very clearly mark what you're spinning around, because we can change it. We can spin around the x-axis, the y-axis, or any horizontal or vertical line. So I read through and I see that it's telling me we want to spin around the x-axis, so I usually make a little kind of curly cue to kind of indicate to me which way I'm spinning. Now typically when you do this, what you're going to want to do is when you spin, realize that you're creating a mirror image. You're spinning this around. There's always going to be the top half and the bottom half. So usually what you do is you then come in and you draw in your bottom half, and if you want to, you can dot it in. You just need something to show where the bottom of your figure is going to be when you spin. I also like to, I wouldn't worry about it here because we're starting at a kind of point, but anytime there's a wide area that you're spinning around, I like to take the points and say, well, if I spin this point, it's going to spin around to here and then spin around to here. So I try to make it look three-dimensional so I can see this idea that the actual figure that I end up with is sort of this kind of ham-shaped three-dimensional object that I'm looking at right here. So I and sometimes if you shade a little bit, that helps you kind of see where you're looking at, and that this is the end of it, that kind of looking in on it. I also like to put in, because it really, I think, helps you, that remember, you're always going to slice perpendicular to your axis of rotation. So putting in that one representative slice is always kind of nice to kind of show, just like we did with the rectangles when we were doing the area, that this is how I sliced it. And so this is what I'm going to find the actual area and volume of by doing area of the base times its width, and that's what I'm going to sum up. So I start by finding the area of the disk as a function of x. Now how do I know that I'm doing this as a function of x? Because I know that the height or the width of that prism is going to be dx. And as soon as I see dx, I know that my bounds are x values. My width is with respect to x, and my area of that face of that prism has to be in terms of x. And remember, that area is always a circle, so it's always going to be pi times the radius of the disk squared. And so our job is to find the radius and figure out what it is in terms of x. Now usually it helps to draw it on and say, well, here's where the radius actually is. This is that r on that representative disk. And so I start looking around and going, how can I get that as a function of x, and I realize that this radius is exactly the y value. So in this problem, the radius of the disk is the same as the y, but I need it in terms of x, which means I need it as square root of x. So the area as a function of x would be pi square root of x squared. My bounds, I went from 0 to the 1. That was where we ended the curve before we spun it. So my bounds are 0 to 1. X values, x values, x values. So my volume, I add up from 0 to 1 all of the areas times dx. That's how I get my volumes. And we can go ahead, because pi is always a constant, they just like to pull it in front, 0 to 1, and square root of x squared dx. And then from there, you would just calculate the actual value. I'm going to not focus on that for this lesson, because I really want to get focused on the picture, determining your area of the base, your width of the base, and then the bounds, so that you can write this part. The rest of this is really just back from a previous chapter. So I'm going to leave you to finish out the actual finding what the volume is. When I post my key, I'll have an actual solution to it. All right, and the big thing to remember in this problem when you are sketching, that you are always going to slice it perpendicular to your axis of rotation. And when you are slicing, okay, if you are slicing vertically, then you know that everything is going to be in terms of x. If you slice it horizontally, everything is going to be in terms of y. Vertical lines are x equals, horizontals are y equals. But remember, your axis of rotation is perpendicular to these two statements over here. All right, let's take a look at the second example. And this is where it starts to get a little fun. So we're going to start the same way. It's always start with a sketch of the region. So it's pretty much the same skill set that you had back in 7.1. So I still have my square root of x. So I'm going to add that in. All right. We have x equal to 0. Now x equal to 0, that is your y-axis. So I'm going to kind of just draw that in, so I keep that as a boundary, my y-axis. And then the line y equal to 1. So y equal to 1 is right here. So that's the line that I'm basically looking at. Okay, and they do kind of intersect up there. So there's my y equal to 1. So the region that I am trying to spin is going to be this region right here. Okay. Now be very careful, pay attention to what you're spinning around. There's no rule that says I always have to spin around the x-axis. In this problem, what I'm actually spinning around is the line y equal to 1. The line y equal to 1. So when I do this spin, see if I can move all of this down. Just give myself a little bit more room there, and you're probably mad at me at this point because you can't move yours down. So I'm going to do the spin. Now when I do the spin, I do want to try to do the other half of it, because remember, you're spinning it around. This is what I'm spinning. So when I spin it around, you kind of go, well, there must be a mirror image up here. So I'm going to go ahead and extend this out and draw the mirror image. So I always draw the mirror image. Gets me the top half. And then I kind of show the spin on whatever open end I can. So this would be the spin. And you can kind of see it looks a little bit maybe like either a dunce cap or maybe a Hershey's Kiss of some sort. That we have this three-dimensional object that we're spinning around. And I like to draw my little shading here going this way because we are going to slice it. Okay, going back to the slicing idea, that we slice it perpendicular. So my slices, when I slice, to get my disc, are going to be vertical slices. As soon as I see that, I go, hey, my width is going to be dx. I'm going to need the area as a function of x. And I am going to need my bounds as x values. My bounds our x values. Okay, so even though I didn't rotate around the y-axis, I rotated around y equals 1. And but the difference is when you look at this, you still get the same idea that we're going to slice it into our little prisms and we're going to add them up and we're going to do a Riemann sum and we're going to get a definite integral. We know we're doing dx. Now we need to figure out our bounds and we need to figure out our area as a function of x. Now again, area is a function of x. We know the area is circular because it's a disk, so we need basically the radius as a function of x. Now I'm going to start with that, and I'm going to be very careful. Now, one of the comments that I will make about being careful when you do this, always draw your radius to the known function, not to your mirror image, okay? So I'm going to put r right here on this figure. Go from known to known, boundary to boundary, in the shaded region that is what you started with, the thing before you rotate it. So that's my r, okay? And your job is, now you have to find r in terms of the region that you started with. Now remember, top minus bottom. I can't say that enough. When I do this r of x and I put it in, because area is always positive, because this is an x, I need top minus bottom. So I need the top. The top is y equal to 1. The bottom is the square root. So that radius, which is the height of the little region right there, is going to be 1 minus square root of x. 1 minus square root of x. All right, then I need my bounds. Well, the easy one is starting at the y-axis, so we're going to go from 0, and then here I need to figure out this x value. And remember, what do we know? We know it's the intersection of square root of x and y equal to 1. So square root of x equals 1, x equals 1. So we're going 0 to 1. So the volume is going to be, and we always kind of take this and pull the pi out. Pi, definite integral, my bounds 0 to 1, my radius 1 minus square root of x squared with my width dx. So I sum the area of the prism times the width of the prism from 0 to 1, and we turn it into a Riemann sum. Again, I am going to leave this for you to finish, and when I put my key up, I'll show you the answer. All right, let's take a look at example 4. And like I said, I'll show you the answers to the actual volumes in the notes when you look at them, but this is about getting the region, rotating the region, and setting up your definite integral. So we're going to find the volume of a solid. We're going to rotate the region bounded by x cubed, y equals 8, x equals 0, about the y-axis. So I'm going to start with the sketch, just like we did with the section 7.1. I need to go all the way to y equal to 8 for one of my boundary curves. So let's make this pretty small. 4, 5, 6, 7, 8. So there's my y equal to 8. Okay. I need x equal to 0. X equal to 0 is the y-axis. Let me change color so I don't lose which my functions are. And then this axis, that was very bad. So this is going to be one boundary. And then we have a cubic. So 0, 0, 1, 1, 2, 8. And yes, it does continue down that way. But the region that I'm interested in is going to be this region. So I kind of shade that in. And now I'm getting ready to rotate. I look back and I say, where am I rotating around? I'm rotating about the y-axis. So here's my y-axis. I show that I'm going to rotate around there. And if it bothers you, because it might get a little busy up there at the top, let's rotate it around here, just to kind of show that. And when I rotate, I come in, I'm going to show the other half. I'm thinking about what I'm rotating around, so I think, oh, this is going to have a mirror image over on this side. I really don't need the top part because I'm only rotating this little yellow piece. I draw in to kind of show it, make it three-dimensional. So that would be this. And now I need to remember, you always slice perpendicular. So because my axis of rotation is now vertical, I'm thinking to myself that I'm slicing it horizontally now. So when I draw in my representative little slice, I'm going to draw the representative little slice in so that it is horizontal. And so the disc that we're looking at now is going in a horizontal fashion. As soon as I see that, because I went perpendicular, so I'm slicing horizontally, I know that that is going to have a dy, that I'm going to need my area of that face of the disc as a function of y, and I need to know that my bounds are y values. Okay? Pay attention to which way you rotate, and the way that you rotate tells you what variable you're going to have in your volume formula. All right, now, so the bounds I can get pretty straightforward because the y values are running from 0 to 8, so I can add that in down here. Oops. All right, we've got the dy. Now we need to find area as a function of y. Again, solid of rotation, it's always pi times the radius, but now it's a function of y squared. Our function of y, now I draw it in, remember, draw it in the region that was shaded originally. Here's my r that we're taking a look at. How do I find this r? Well, that r is exactly the x of this. But remember, I only know this as y equals x cubed. I really need it as x equals cube root of y. Change your perspective. We're now basically doing right minus left. The right is the cubic, the left is the axis, which is 0. So my r of y in this problem is going to end up being pi times the cube root of y minus 0, technically. And then, of course, we have r squared in it. So our volume, once I get all this information down, my volume is the definite integral. Pull the pi out, it's just standard notice, from 0 to 8 of that radius I found as a function of y squared times dy to get it in units of volume. And again, I'll leave this for you to finish out and get the actual volume. All right, let's take a look at the next idea, that whenever we go to do this rotation, depending upon whether or not the region that I'm rotating is kind of attached to the axis of rotation, or whether there's a little bit of a gap there, that when I spin it around, instead of getting a disc, we're going to get a washer. Okay, so I'm going to highlight the word washer. A washer is nothing more than a disc with a hole in it. So when we are doing our area, okay, our prism is basically, you've got to take the big prism area minus the hole. So it's the whole thing minus the hole. And notice that I've got capital R goes all the way out to the edge. Little r is going to go to where the hole is. So we have two different radii that we're talking about when we're doing a washer. And a lot of times what we see when we do this problem, we like to pull the pi out. So you'll see it written as pi times the difference in the radii squared. Pi times the difference in the radii squared. But I'm basically taking the area of the big minus the area of the small. So we want to keep that in mind in that situation. So this is what's called the washer method. The washer method. So this one is specifically for when I am rotating it around. So usually what happens here, okay, you're going to have two functions. You're going to have a function f, and you're going to have a function g. And what you're rotating around, the region, when you go to rotate it, you'll see that the region doesn't actually touch its axis of rotation, that there's kind of a gap right here. So when I go to spin this around, and you know, the idea is you try to visualize with me, that this one will spin around to here, this one will spin around to here, and that what you get, the part that's solid in your disk, is going to be this section. And of course it's got some width to it when we spin it around. So that since this is the solid portion, actually let me do this because I don't like having, I like to have, I'm one of those artistic people, I like to have, undo, come back. Alright, so let's put my width in. I like to have some shading in for that. So that's solid, and then maybe that will help you see kind of what we're looking at. That we have a solid washer, and that my washer has a hole in it. And so basically each time you do this, you're going to need to calculate your little radius is the hole, usually to G. Your big radius goes all the way to F, and you're taking the difference in the areas, the big area minus the little area. Okay, so this would be when and notice that we are still slicing vertically because it's perpendicular now. Mostly washer needs a hole in it. So you can see the difference. If I was going to do the same problem, but instead of going around, say, an x-axis, suppose I went around the y-axis. So here's a y-axis, and we might spin around this way. Let's take our region, and again, our region is going to be left and right this time. So when I spin it around, you end up with, remember you always do the mirror image over on the other side. I didn't show it here, but technically there's a mirror image of G, which ends up there, and a mirror image of F, which ends up there, and that's why you're getting this three-dimensional shape. So if I take this and I spin it around, here's my mirror image, there will be a hole, and then there will be a bigger part, and we do get that idea of a washer. Now if I spin this way, it's always perpendicular, so because my axis of rotation was vertical, I'm slicing it horizontally. This will be dy. These will be areas as functions of y. So the volume in this case would be pi c to d, because I'm doing y again, and it would be r of y squared minus little r of y squared and dy. That would be the only difference if I spin that way. Okay? So let's take a look at the washer method. So we take a look at this. We already have our figure, it's already drawn for us, that's very nice of them. We're in the first quadrant enclosed by the y-axis, cosine, and sine. And hopefully you know that this one's the cosine and this one is the sine of x. And we are spinning it around the x-axis. Okay? So we're going to spin it around the x-axis. And when I do that, and again, how do I get a picture? Give yourself a mirror image of each function. So I'm going to draw the sine x mirror image down here. I'm going to draw the cosine x mirror image. Just think of it like a mirror. Any type of opening, like this gap right here, this point right here was spun around, so I kind of draw a little circle to do that. If you want to think of this as your end, and then usually this has an open side over here too, so that point kind of gets spun around, and then sometimes I kind of dot it in behind because I want to show that that's behind the figure, and you can start to see that you kind of have a figure that looks like this. Sometimes it helps to go and use some of the items that I've given you. Let's see if I can go here. Alright, I'm going to look around and see if I can find a good animation software for this, but for right now, you know, this is partly why you really kind of have to have a pretty good idea of when you're sketching these, that you're trying to get it so that you can really just understand what's going on. That we have this solid, if I kind of show that I have this part of it, this solid portion right here, and that back in the background, that this right here is really a hole located in the figure, and that if you kind of look down, stand over here and look down, this goes all the way through the figure that you're going to have this missing section that you have there. Now when you draw your kind of representative slice, remember it's perpendicular, because I know I have a hole. You have to recognize you have a hole in this problem. So when we draw our representative slice, I am going to go from the top all the way down to the bottom, okay, to get kind of the outside edge of my washer, and then kind of draw the back side in. And then I'm also going to do the same thing right here, that I'm trying to show that we have this hole in it, and you kind of try to do some shading to see what you're doing there. So, and we also know that this is dx. I recognize that this is a washer, that my solid rotated figure has a hole in the middle of it. That's really the only reason why I'm drawing this in. And that what I need to do is I need to take the area of the big one minus the area of the little one in order to get the actual area of the disk that we're looking at. And it is a function of x because I'm dx. And my bounds are x as well. Okay, let's start with the bounds. That clearly we went from 0, because I'm with the y-axis, up to where cosine and sine intersect. These are the two functions that I started with. This is why you always have to remember, and you'll start to see this also, make sure you're paying attention to the region you rotated to start with. It can kind of get kind of hinky in here when we're taking a look at it. We'll start to lose a little bit of the detail. This is what I was rotating. I need this intersection point. I need to know when cosine of x equals sine of x, and hopefully you know that that's at pi over 4. So I got my bounds. I know it's dx. Now I need to do this part. I need to get my radii. I know that I'm going to have pi times the big radius squared minus pi times the little radius squared, and that those radii have to be in terms of x. Now when you draw your radii on, be very careful. The big radius, you might as well just go ahead and start with that. Make sure you go to the outside of wherever you are, and you go to the shaded region. Even if the shaded region is down here, you go to it. So I go from axis to all the way to the outside, wherever the shaded region was. That is my r of x. So hopefully you're like, hey, wait a minute, that's cosine. So over here, this is going to be pi times cosine of x squared. All right, minus pi times the little radius. So I'll pick a different color. I don't know, I'm starting to run out of different colors. Let's do this blue. The little radius is this portion right here. So little r. That goes to the inside, the bottom function. And that bottom function is the sine function. So that would be my sine of x squared. So the big thing is really just figuring out where your radii are and getting your picture in these problems. Once you have this stuff written down, you're ready to go. Your volume is going to be the integral from 0 to pi over 4. We know we're doing washer. We pull the pi out. We take the radii, square it, and take the little radii and square it, and we put in our dx. And again, I will leave this for you to kind of wrap up and do on your own and check your answer with the key. All right, let's kind of wrap up where we are with the washer method. Important things to consider. Always, always, always draw your picture. I don't like that color. Let's undo that. And the picture is what's really going to help you set up the situation. Okay? Your cross sections must be perpendicular to the axis of rotation, perpendicular. And before you write an equation for your big R and your little r, put them on there and make sure that when you draw them, okay, you always draw them from your axis to your given functions. To wherever your region was, you want to make sure that you always go to the outside of the region to in the inside of the region that you shaded but that you actually rotated. All right. We still want to make sure we're doing top minus bottom, which is why this is big R and little r. Big R will always go to the farthest distance away. Little r will always go to the smallest distance. If we're going left and right, right minus left, top minus bottom, right minus left. And in each of these cases, because your radius goes from the axis of rotation, the left or the bottom is going to be the axis of rotation. Maybe. Could be the top too. Don't forget to square each radius because it's pi r squared, and do not do this. This is wrong. I am going to put a big circle on this, and I'm going to do a very, very bad math thing. This is not true. R squared plus little r squared does not equal this squared. This goes all the way back to Algebra 2. Powers do not distribute. Do not make this mistake. It's the difference in the areas, which is pi r squared, not r plus r squared. It's a subtraction. You want to make sure you do not distribute the powers. Do not distribute the powers. I cannot say that enough. Do not distribute the powers incorrectly when you're doing this. Okay? Now, what I would like you to do before you come to class on Monday, Tuesday is, based on the information that we've done, and I'm not going to do the video for this yet, but what I want you to do is I want you to do example 6, just these 5 problems, and I want you to come to class with a good sketch, and I want you to put them on your own paper because there's not enough room. Put on your own paper, and I want you to have a very nice sketch. I want you to identify the areas, whether they're function of x's or y's, and very clearly, just like I did, your dy dx and your bounds, whether your bounds are x or y values, and write your formula for calculating the volume. And then I actually want you to go through, and for each of the ones that are in this packet, I want you to actually calculate the volume. So actually go all the way down till you get your answer. And that's what I'm going to be checking in class next time. And we'll go over the answers and see how you do on that. So this is where I want you to stop based on what this video is.